Hello everyone. Today we're going to discuss chapter 4, which is the finite element method. It's one of the most important chapters of the computational technique course. I have already discussed about the general outline of the finite element method in chapter 1. Here we're going to dig a little deeper into the concept of finite element method. So here basically finite element method is a tool or a method which is used to solve problems related to engineering and mathematics. While solving these problems, when you are looking at the analytical solutions for the complex problems, which include complex geometry or complex loading and different material properties, generally involve a complex solution in the form of probably partial differential equations. Now, to solve these partial differential equations is difficult, whereas when you are looking at some elements such as trusses or beams, columns, frames, or some kind of plates, we can solve these by making some assumptions to simplify geometry and the loading conditions. For example, if you have a beam that is like this, we can simplify this beam into a line segment like this, which is generally easier to solve rather than this one. Now these solutions are not exact, they are approximations. These are approximations at certain discrete points. Now these approximations can be of the displacements or maybe of forces at these nodes 1, 2. If you have a beam like this and you have a load which is a UDL going like this, and let's say this is hinged and this is a roller, then what you'll have is this beam will deflect like this. Let's say this is the exact solution that you're looking for. Now in FEM, as I said earlier, that the solutions are the approximations at certain points. For example, let's say you are only solving at this, and this point. Then what you'll get is you'll get a value of displacement up to here. Now when you connect these points, you'll get a curve like this, which is a linear rather than a curved one. Here you can see that the red line is an approximation to the blue dotted exact solution. Now when you increase the number of points of the solutions, then you may get a line which may correspond closely to the blue line. Therefore, the sensitivity or the accuracy of the solution depend upon the number of nodes you have, the number of points you are solving in a body or in an element. Now, as you can see above, that we have a beam which has been discretized into different segments by these nodes. These are called nodes, and these parts here which are separated by the nodes are called as elements. Now you can see that in this beam there are finite number of elements. So there are 7 number of elements and there are 8 number of nodes. The procedure of the finite element method is something like this. You take each of these elements out. So you take the first element out and you form a free body diagram like this. Now this is your element number 1. Now here you'll have 2 nodes and this will be your beam. Then you have to solve for your forces and your displacements or the moments at these nodes. Let's say this is node 1, this is node 2, this is your node 1, this is your node 2. Again, you take another element which is element number 2 like this, and then this will be your node number 2, this will be your node number 3, and then you also solve for your forces and your moments for element number 2. Similarly, you solve for all of your elements and then you reach element number 7 at the end. And then what you do is you combine all of these solutions to obtain your final solution. Now this combination depends upon the numbering of the nodes. So therefore we have to be careful about the numbering of the nodes or the elements. This will be clear once we move into the numerical examples. So the basic steps involved in the finite element analysis are: number 1, we create a part or element. For example, let's say you are going to perform a shear test in a plate like this, where you have a hole and there is a bolt that is going through here, like this. Now what you are going to do is you are going to perform a shear test by fixing the plate and moving the bolt across this side. Now this will cause the plate to deform, maybe something like this. The hole may get stretched like this and your bolt will reach here, because generally the bolts are stronger than the steel. They are generally of grade 800 MPa, whereas the plate may be of 250 or 550 MPa. Now to do this, you have to form 2 parts. You have to form a plate and you have to make a bolt. So this involves making 2 parts. This is part 1, that's part 2. This is actually a procedure in FEM softwares, whereas in theory, when you are solving for a beam like this, then you just form a part that is linear like this. So this is your line element. Or you may actually have a truss, then you form line elements going like this. So this will be your truss. Now the second step is to mesh it, meshing, or discretization. Now, as I explained earlier, that the solution of the FEM is obtained at different nodes. Now, to create those nodes, we have to discretize or mesh our structure into different elements. For example, in this one, what you can do is we can discretize this into different squares like this. Or cuboids in 3D. Then each of these intersection points will serve as a node. Therefore, we'll obtain solutions at these number of nodes. Similarly, for the bolt as well, we may have to discretize it like this. So each of these intersections will be a node. Now in theory, what to do is, if you have a beam like this, then you may discretize this beam into 4 different elements like this. Or if you have a truss, you may discretize it like this. So each of these truss members will be one single element, and then you can solve for your nodes. So you can solve your displacement and force at each of these points, and so on. Third part will be material property specification. So the third step is generally to provide the specifications of the parts you have created. For example, if this beam is steel, then you got to assign your Young's modulus as 200,000 MPa. If this was concrete, then it will be 20,000 MPa. Similarly, there are different properties that you can assign. It may be Poisson's ratio as well. So in truss also, you may have to specify your material properties, which may be concrete or steel or some other element. Now the fourth step is to derive the element equations. Now for these each separate elements here, you have to obtain your equation, which may be in the form of stiffness matrix. And then the fifth step will be to assemble the element equations to form a global system. Now once you have obtained all of your stiffness matrices, then what you do is that you find a global stiffness matrix, which will be summation of your individual element stiffness matrices. Now this combination depends upon the degrees of freedom or the numbering of the nodes. In an FEM modeling, assembly means to combine this plate and this bolt to form this assembly here. So this is the assembly of the global system, and then we specify the boundary conditions and the loading conditions. For example, in this case, boundary condition will be this one being fixed, the edges of the plate being fixed, so the plate doesn't move anywhere, and the loading condition would be applying displacement in this direction here and this part as well. There are other boundary conditions here, but I'm not going to go into detail with this one. However, if you look into a simple beam, then the boundary conditions may be something like hinged here and roller here, like this, and the loading condition may be a UDL and maybe a point load here. Generally, what you'll have is, for a global system, you'll get a global force vector which will be equal to global stiffness matrix times your global displacements. Now the boundary conditions may refer to the displacements, because when you see your boundary condition as fixed, you can see that your displacement in this direction, or the rotation are 0. Or for the hinged case, what you'll have is your u1 will be equals to 0, your u2 will be equals to 0, but your theta you may have to figure out. Therefore, the boundary conditions for the hinged case will be u1 equals to 0 and u2 equals to 0. And the force condition will refer to your force vector here. Now these forces are the nodal forces that you'll obtain from your loading condition. For example, in this case, if this is your omega UDL, that's your length, then what you'll have is you'll get your nodal forces in this direction as omega L by 2 and omega L by 2. So this will be your force at this node, and this will be your force at this node. So your loading condition will refer to your force vector, and your boundary conditions will refer to your displacement vectors. And the relation, the mathematical relation that links these two vectors is the stiffness matrix. So this stiffness matrix is very, very important. Then you solve the assembled equation to obtain your displacements or forces. It may be stresses, strains, and so on. What this means is that once you have assigned your boundary conditions, let's say you want to find your displacements, then what this equation gives you is your displacement vector equals to your inverse of your stiffness matrix times your force vector. Let's say you know all the values in the force vector and you know your stiffness matrix, then you can solve for your displacements. And after you have known your displacements, then you can find your forces as well, and so on. So this is the general procedure of solving a finite element problem. Now we are going to look into the direct stiffness method. Before moving into this method, please go to my lecture 1 and get a general understanding of degrees of freedom, nodes, and elements. I can just brief you about degrees of freedom. Now, degrees of freedoms are the number of independent displacements or rotation that describes the structure. For example, for this one, the degree of freedom is only 1 in this direction. For this kind of boundary condition, the degree of freedom will be 0. Now let's move into the bar element. Now, bar elements are those elements in which the load is actually applied, which means they will only elongate under the applied load, or they will compress or shorten under the applied loading. This is the tensile load and this is the compression load. Now here, if the original length of the bar element is L, and let's say this one increased by delta L under the applied load of F, then we already know the Hooke's law, which says that your force equals to kx, where F is your force, k is the stiffness, and x is the elongation in the direction of the loading. Then what you get is x equals to F by k. Now your x equals to delta L here, so we get delta L, which is elongation here, equals to F by k. Now we have to find what is k. We have a relation between stress and strain from the strength of materials, that your elastic modulus equals to stress by strain. Now in the figure above, if this was area A and this is your force applied, then your stress will be force divided by area. Now according to the definition of strain, your strain will be increase in length divided by the original length, where L is the original length. Now from here, what you get is your delta L will be equal to F L by A E. Now when you take L below, you will get F by AE by L. Now you can equate this with this, so you can see that your K equals to AE by L. Let's take this bar element again. You can see here that there are two nodes, node 1 and node 2. Therefore, you'll be solving for forces at node 1 and node 2. Let's say the force at node 1 is F1 and force at node 2 is F2. Similarly, you'll also be solving for your displacements. So let's say your displacement at node 1 is U1 and at node 2 is U2. Now the question here is to link force F1 to U1 and U2 and to link force F2 with U1 and U2 as well, because the force F1 will have its impact on U1 and U2, and force F2 will also have an impact on U1 and U2. Therefore, we have to find a relation that links these. Now this relation is the stiffness matrix. Generally, the size of the stiffness matrix will correspond to the number of nodes you have. Here you have 2 nodes. That means your stiffness matrix will be of size 2 by 2. Now the procedure to find the stiffness matrix is like this. What you do is we hinge one end or fix one end and apply a loading of F1 at degree of freedom 1. F1 applied here, which will induce displacement from here to here. That will be U1, and then on this side you will have a reaction, that is F2. Now what will happen is your F1 here will be equal to AE by L. And if you use the equilibrium equation, you'll find that F1 must be equal to F2, but in the opposite direction. Therefore, your F2 will be equal to AE by L again. Sorry, into U1, because your force equals to K times X. Here also it will be equal to U1. So this will show an effect of force and displacement and force F2 and displacement 1, or the relation between F2 and U1. And again, for the other part, what to do is we fix the degree of freedom in this direction and then apply displacement or force in this direction, that is F2, right? This will induce displacement here as U2, and this one will have a reaction, that is F1. Here U1 is automatically 0 because this is hinged and we are locking the degree of freedom. Therefore, here F2 will be equal to AE by L times, this is L, times U2, and according to the equilibrium equation, your F1 must be equal to minus F2, which will be equal to minus AE by L times U2. Now this one gives a relation between F1 and U2. Now let's write these equations. These two equations will have F1 equals to your AE by L U1 from here plus F1 from here, which equals to this one, so it will be minus AE by L U2, and your F2 will be equal to, from here we get minus AE by L U1, and then from here AE by L U2. Now you can write this in a matrix form where you'll get F1, F2, which are your nodal forces, will be equal to AE by L minus AE by L minus AE by L and AE by L U1 U2. Now you can take AE by L common from here, then what you get is AE by L 1 minus 1 minus 1 1 and U1 U2. This is F1 F2. Now this is your force vector, that's your stiffness matrix, that's your displacement vector. So there you have it. This is our required equation which relates your forces and displacements in a bar element. Now let's look into an example comprising of the bar elements. Let's say we have beam which is fixed at two ends like this and has bars like this. That's the first bar, a fourth bar like this. Let's say this bar has an area A. This bar has an area of 3A by 2. This bar has an area of A by 2. And this one also has an area of 3A by 2. If you want to look at it more realistically, what you'll have is this as a whole system comprises of different sizes of bars. If you put nodes here, let's say this is node 1, 2, 3, 4 and 5. Node 1, 2, 3, 4 and 5. Then these will be acting as separate elements. So this will be element number 1, this will be element number 2, 3 and element number 4. And let's say each of them have equal length of L by 4. So the total length will be L. Let's say we apply a force of P at this point here. That's your loading condition. Now based on this, you are asked to solve the displacements at node 2, node 3 and node 4. So that will be U2, U3 and U4 are what? Let's go into the procedure now. So you can see here that we have already created our parts or elements. Let's say each of these have same elastic modulus of E. Then let's look into element number 1. So for element number 1, this is your node 1, this is your node 2. So for this one, you have to form your stiffness matrix. So this is element number 1. And as you all know, our stiffness matrix will be given by A by L. And we'll have 1, minus 1, minus 1, and 1. But you can see here that the length of each section is L by 4. So we just put L by 4 here. And area is A for this element. Therefore, A by L, this will be 4 minus 4 minus 4 and 4. So this is your stiffness matrix for element number 1. Now let's look into element number 2, where this will be your node 2, this will be your node 3, and this is element number 2. Now for this one, your stiffness matrix will also be equal to A by L, but you can see here that the area here is 3A by 2. Therefore, we write 3A by 2 and then L by 4. Now when you simplify this, this is number 2. Similarly, your K3 will be equal to, and finally your K4 will be equal to, let's say this is 3A by 4. So we have different values here. Now what we'll have here is, we'll have 3A by 4 E L by 4. Now we have stiffness matrix of each bar element. Then what you have to do is to assemble these to find the global stiffness matrix, which will be a summation of these individual matrices. Now to find this, we have to take care of the degrees of freedom. Now here, this is our degree of freedom U1, this is U5, 2, 3, 4, 5, right? You can see here that this is corresponding to U1 and this is U2. This is corresponding to U2 and U3. Similarly, it will have similar configuration for the other elements as well. Therefore, when you write this, it is easier if you write the degrees of freedoms at the top. Let's say this is degree of freedom 1, this is 2, 1, 2. Similarly here, this is 2, 3, 2, 3. This is 3, 4, 3, 4. And this is 4, 5, 4, 5. Now, when you are obtaining the global stiffness matrix, what you do here is you write all the degrees of freedoms here. So there will be 1, 2, 3, 4, 5, because we are looking at the system as a whole rather than elements. So we'll have 1, 2, 3, 4, 5. Here also we'll have 1, 2, 3, 4, 5. Now in these areas here, you can see that this one corresponds to 1 by 1, degree of freedom 1 and degree of freedom 1. So when you go up here, you find your 1, 1, which is this one here. That's your 1, 1, right? So you take that and put it here. Let's fill the rows first. So, and then you go to 2, 1. So what you find here is this one corresponds to 2, 1. Therefore, you write minus 4 here. And you can see that there is no 3, 1, 4, 1 or 5, 1. Therefore, you write 0, 0, 0. This just means that when you are solving at each element level like this, let's say this is 1, 2, 3, 4 and 5. When you are obtaining this solution, you're actually fixing all these boundary conditions. Therefore, the displacement you give here will only have a reaction force here, and this force won't transfer to these nodes. Therefore, you'll have 0 values there. Similarly, let's look at the second row. For the second row, you have to look into 1, 2. So you get this one here. So you write minus 4 here. And now, when you're looking into 2, 2, you'll see that this is also 2, 2. And this is also 2, 2. Because this is a common node between this element and this element. This is a common node. Therefore, you have to add it up. Now, what you get here is 4 plus 6, isn't it? So it will be equal to 10 here. And now you will be looking into 3, 2, which will give you minus 6. And this will not have an impact on the other nodes. It will be 0, 0. This just means that when you are loading this point here, you are fixing this, but you are applying a force here, which means that this is going to have an impact on 1 and impact on 3. Therefore, it will induce a force at F3 and induce a force at F1 as well. Therefore, we have 3 values here, and these all must be in equilibrium. Therefore, generally, when you are only looking into forces, then the sum of each row should be equals to 0. When you have a common variable outside, you can see that these will be additive. Now, when you add this in an equilibrium condition, your F2 will be equal to sorry, f1 will be in this direction. So f1 plus f3 should be equal to like this. So therefore, when you add these up, so f1 plus f3 minus f2 will be equal to 0. So therefore, when you add these up, they must be equal to 0. But this may not apply in all the conditions, because you may be looking into different degrees of freedom. For example, if you have rotation somewhere here, then the sum won't be equal to 0. Now for the next one, you can write here directly now. The 3, 1 here is equals to 0, and 3, 2 will be equal to minus 6. You can see that there are 2 3 3's here, this one and this one. So add those up, you get 8, and then there's 1 3 4, that is minus 2, and there's no 3 5. So for the fourth one, 1 4 equals to 0, and then 2 4 0, you go 3 4, you get minus 2, and then 4 4, you can see there are 2 of them, so this will be equal to 5, and then you go to 4 5, this equals to minus 3, and finally 1 5 0, 2 5 0, 3 5 0, 4 5 you have minus 3, and 5 5 you have 3. So this is your global stiffness matrix, where you have a common here, A by L. Now you can see here that the summation of each row equals to 0, and this is also a symmetric means that the corresponding values above and below the principal diagonal, which is this one, are equal. For example, your 4 3 must be equal to 3 4. So symmetric means you have your element Aij, which is row, this is column, equals to your Aj only for I not equals to j, because I equals to j will be your principal diagonal. So this is your stiffness matrix. Now we write our global equation. Now you can see here that there are 5 nodes, so there will also be 5 forces acting in this direction. So you will have your force acting here as well. This will be P1, let's say F1, F2, F3, F4, and F5 in this direction. We are taking this direction as positive, which is the direction of the displacement taken as positive. Now your equilibrium equation will be F1, F2, F3, F4, and F5 equal to AE by L. Then you'll have your global matrix and your displacements. Now after you form this global equation, now it's time to put our boundary conditions. Now the boundary conditions here will be, you can see here that U1 here and here are fixed. That means they won't be able to move in the actual direction. Therefore your U1 will be equal to 0 and U5 will be equal to 0. Now this is your boundary condition. Now if you look at the forces, you can see that the forces at F3, as there are no forces applied, it will be 0, F4 will be 0, and F2 will be equal to P, because we are applying a load P at node 2. Now since we know the left hand side values of F2, F3, and F4, then what to do is we separate this out because these are known. So what you write here is should be equal to AE by L. Now here we are looking into degrees of freedom 2, 3, and 4. This is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We are looking into 2, 3, and 4. So to look into this row, this row, this row, or this column, and this column. Then you can just have to shift those values here. We get 10 times u2, u3, and u4. So this is 2, 3, 4, 2, 3, 4. Now we can directly solve for our displacements. Therefore, your u2, u3, u4 will be equal to L by AE times inverse of this matrix times you get P 0, 0. What you'll get will be, if you want to find your forces or reaction forces at F1 and F5, what you got to do is you got to take these values and put it right here. So you form this huge matrix and you solve for your F1 and F5. Then what you will get will be, so these will be your forces. So this is how we solve for unknown forces and displacements in a bar element. If you want to look into further examples of this type of equation, this type of formulation in the bar elements, you can go to my another playlist which is on the abacus. You can go to chapter 1, springs in series, and rods in series. This is in another playlist where you will understand how to use abacus. You'll be able to observe the solutions in the result simulation as well. What I have done there is I have solved numerical examples on the bar elements and then modeled it in a finite element analysis program called abacus, where we visualize and verify our results. So this was all about the bar elements. In my next video, we'll be learning about inclined bar elements which form the trusses. Thank you for watching till the end.